Welcome to our presentation of the TMLR publication, Active Learning of Ordinal Embeddings, a user study on football data. This work is a collaboration of FAU, Fraunhofer IIS, and Georgia Tech. My name is Christopher Löffler, and my co-authors are Kion Falla, Stefano Feno, Dario Zanca, Björn Escoffier, Christopher Rosell, and Christopher Mutschler. This talk introduces the soccer application in previous work. Then I explain how we may learn an ordinal embedding from annotations. Finally, I will present the results of an active learning user study. On the right, you see the soccer application as an example. Our motivation is the information retrieval in large soccer datasets. Concretely, we search similar scenes in sets of trajectories. See here on the right, for example, two scenes that appear similar from different games and different teams. The users of this technology can be trainers, for example, that want to quickly look up previous games. They may ask questions like, where did my team face the situation before? The dataset we use is provided by the Deutsche Fußball-Bundesliga. It consists of player and ball trajectories that were all extracted from video data. The data itself is sparsely labeled by experts, like with pass events or kick-on-goal events. We cut out the data into windows of 5 seconds length, and this way we get around 1.2 million data points that sadly have a very high dimensionality of about 8,000 values per sample. So because the labels are so minimal, we estimate the similarity between samples not by labels, but by using an Euclidean distance between two of these data points. However, this does suffer from the curse of dimensionality in multiple ways. First, we assign players between scenes, as you can see here below. And this is not a given information, since there is no order known. Shirt numbers are not really suitable for this. And second, we are calculating Euclidean distances on this very high dimensional data. So both of this together means that the calculations are prohibitively expensive. Our previous method solves this by estimating the assignment that you saw between players and the similarity of two scenes via a Siamese network. Here on the right, you can see a visualization of that. For that to work, we created training data for supervised learning by first solving the assignment problem and calculating the distances as targets. Then we trained the Siamese networks with the approximated assignment instead of the predetermined optimal assignments. And third, we use this loss to minimize the differences between the distance in the embedding and the real-world distance. So to summarize the previous work essential basics, this approach has some benefits. First, the most important one, it's really fast, it's less complex. But one downside is that the Euclidean distance as a similarity measure is suboptimal. Third, the embedding that the neural network learns is of a slightly lower fidelity, especially in the local neighborhoods or nearest neighbors. We refer to the linked papers for details. So this raises a problem. Can we improve the similarity function that we used for learning? The main problem is that the top k neighborhoods, or the nearest neighbors, they should be more similar, subjectively more similar. And the deficit that we identify is the Euclidean distance that reduces the information a lot. Instead of programming now a detailed similarity function using domain expertise, we hypothesized that we can instead ask human annotators to provide their subjective similarity function to us, their perceived similarity between two given samples. So similarity can be learned from relative comparisons, as you can see soon here. We may use a triplet loss. We have an anchor sample, and relative to that, we have a negative sample and a positive sample. The learning step then minimizes the distance between the anchor and the positive sample and maximizes the one between the anchor and the negative sample, as you can see here on the left. This is the preferred outcome of this exercise. The second important thing that we employ in this study is active learning. So active learning promises to accelerate the learning process by selecting only the most informative samples for learning. We are using InfoTuple here as in queries with query size more than 3, so not just triplets, but larger samples at a time, and this provides also larger context to the annotators. Below here you can see the central formula. So InfoTuple selects a query Q n at the time step n that has a very high entropy. Now, this is the entropy given previous answers, so responses are Qn minus 1, so time step before. For that we expect more consistent responses from the oracles, given a similarity matrix. For details, we refer to the original publication by Canal, Feno, and Rosell. In this publication here, the code is computationally optimized and, for example, uses Monte Carlo sampling to estimate these statistics. And furthermore, we reduce the sets of possible queries, Qn, with a nearest neighbor sampling method. So we design our user study to answer these 3 research questions. So first, how consistent and reliable are our participants given this data? This is a baseline question that we have to answer. Second, what is the best baseline heuristic to generate tuple queries? And third, does an active sampling method actually perform better than non-active sampling? So on the right, you see the different phases. We have a warm-up phase. We repeat a set of queries twice to measure consistency. We have non-active baselines, random sampling, a mix of random sampling and nearest neighbor sampling, and only nearest neighbor sampling. And we have 2 active learning methods, the nearest neighbor active learning method and the InfoTuple method. We use a pre-trained neural network that was pre-trained on all the games in our dataset. And we use for InfoTuple a tuple size of 9. That means 1 anchor and 8 samples. We perform our study on one of the games. During the active learning loop, we are fine-tuning the pre-trained model with the annotated samples. Here you can see one example how a query can look like with 8 possible choices and 1 anchor, and the participant would choose one of them. So that means that we can then generate 7 triplets from this one annotated InfoTuple. Let's get to the evaluation. So first, how consistent and reliable are the participants of our study? For that, for each participant, we compare these 2 sets of 20 annotations of the tuple size 9 that you saw before. And the second repetition of this is randomized. So the position on the screen varies so that they don't just remember what they did before. the results show that the annotators exhibit rather high reliability. So the intra-rater reliability is about 0.49 with a low variance. However, we see also two outliers, one very consistent participant and one very inconsistent participant. With respect to the inter-rater agreement, so the agreement between the raters, the annotators, we can make out some pairs and even some smaller clusters of apparent similar functions, similarity functions. Hence, from this we can draw the conclusion that the inter-rater consistency is high, and given the large tuple size, that is not a given. And also that we should investigate these clusters further. To answer research question 2 and 3, we take a look at the gain in triplet accuracy. The slide shows the average triplet accuracy per user on the right side. So we plot the triplet accuracy over the number of acquisitions from 0 to 20. We first warm up the training with the set of 20 annotated info tuples from the first set of repeated tuples, and then we start the respective active or non-active learner. For the non-active baselines, we cannot see a clear difference in triplet accuracy. However, for the active query selection, we see a boost in performance. Here in green, you see the info tuple sample selection. In orange, the active nearest neighbor. And then below, random in red, random and nearest neighbor mix in purple, and simple nearest neighbor sampling in brown. We see info tuple sampling is converging, is plateauing close by the estimated ceiling of performance that we expect if we use all samples that a user annotated over all phases. So this is 0.737. So, however, when you choose an active learning method, there are also other dimensions here that you should consider. First is the time spent per response. So this can hint at how difficult a query is for the annotator. And we see that annotators respond quickly to nearest neighbor samples, quicker than, for example, random sampling. And second, we also take a look at the number of the skipped queries, and they might fatigue participants since they have to annotate more and more samples over time. Yes, and on the right, we show one example of annotated or skipped queries over time, given the various phases that we have in the dataset. And a simple random sampling here, you see, seems very unfavorable, given the total time it takes to just annotate 20 samples, and also there's so many skipped queries in the dataset. So to summarize, in total, our approach is still fast as before, but now we see gains in fidelity, and we deliver a high-quality similarity search result. And we do all this while learning from only few annotations. The queries selected by InfoTuple provide more context for the annotators, and the gains in accuracy are largest for it, while at the same time, nearest neighbor sampling may help to reduce the overall skipping of queries. You can find the code here on GitHub and the paper on Open Review. With that, we end the talk, and I thank you for your attention.